Right, so Volodya asked me to give a repeat of the talk I gave in New York about a month ago. And so this is kind of that. Maybe I'll change a few things here and there. And so for people that were in my New York talk, probably not much is going to be new. Okay, so right. The topic of my talk is the p-adic Simpson correspondence. Everything I'm saying is joint work in progress with Mingjia Zhang. And it very much builds on, or was inspired by work of Ben Hoyer, which I think was discussed in this seminar for a while, quite recently. And so I'll come back to Ben's work later in the talk. But let me begin with, I'm not going to assume you know what he did, and so I will try to present things from scratch in that sense. Okay, so let me begin by recalling the picture of the complex numbers and what we are trying to mimic over the p-adic numbers. So the starting point is this classical theorem of Correlette and Simpson, by now well known, which helps understand representations of fundamental groups of compact Kähler manifolds. So if X is a compact Kähler manifold, then it gives, well, it really lets you understand local systems. So it gives an equivalence of categories between complex local systems on X which is sort of a topological invariant of X, and something that's more related to the complex function theory of X, which is the notion of Higgs bundles. So E comma theta, which is a Higgs bundle on X, and it has to satisfy a condition, so it has to be semi-stable with vanishing Chern classes. And these conditions are not going to be that essential for what we are doing, so I will not spend too much time on that. Let me just recall verbally what a Higgs bundle is. So E is a vector bundle on X, complex holomorphic vector bundle on X. And theta is a map from E to E tensor omega 1, which is O linear. So it's not like a connection, doesn't satisfy the Leibniz rule. It's actually much simpler than that. It's just an O linear map. And it has to satisfy the condition that theta vec theta is 0. So a sort of concrete way to think about this is that it's giving you an action of vector fields on X on this bundle E, and various vector fields are required to commute with each other. I will sort of write that out more precisely a bit later. And so this is a very the first time I saw it, I found it an amazing statement because the right-hand side feels, at least at first pass, much easier to access than the left-hand side using methods of algebra. And so one way to think about what's going on here is that it's a nonlinear version of the Hodge decomposition. So this is a nonlinear or non-abelian, if you like, version of the Hodge decomposition for H1. So if you look at H1 of X with complex coefficients, the Hodge decomposition says that this breaks into two pieces. One is H1 XOX, and the other is H naught of X omega 1X. And this side is a counterpart of this side, and these two sides are counterparts of this side. And one can make that precise by sort of formulating this theorem as an equivalence of moduli space, or as a homeomorphism of moduli spaces. And if you do it like so, then this will be the resulting identification on tangent spaces. So there's a very strong sense in which this is a nonlinear version of the Hodge decomposition for H1. The other thing I wanted to say about the classical story, which just to sort of help pin things down, if you haven't seen this before, is to probably the most important example to keep in mind is the following. So if F from Y to X is a smooth projective morphism, so a fiber bundle, fibers are all projective, then and N is an integer, then you can write down a natural local system on X, which is the cohomology of the fibers, Rn F lower star with complex coefficients. This is an object of the left-hand side. And so it corresponds to something on the right-hand side. And what it corresponds to on the right-hand side is the analogous thing, but now on the other side of So this is some kind of a fancier version of this guy, and what you're going to have on the right-hand side is a fancier version of this guy. So more precisely, what you have is the following. So it's a direct sum over I plus j equals n of Ri f lower star omega j y over x. So the Hodge cohomology of the morphism, that's the underlying vector bundle. And then the Higgs field is coming from the Kodaira-Spencer class, which is the associated gradient of the Gauss-Manin connection. And so this is actually the fact that you get a direct sum over here, as opposed, so it's a graded Higgs bundle rather than just a Higgs bundle, is a reflection of the fact that the left-hand side came from geometry. And so maybe later on in the talk, I'll say a little bit about how this works p-adically, but what I want to emphasize is sort of one way to use this theorem, and this is, I believe, how Simpson first used it, is the observation that on the right-hand side, there is a natural C star action. You can rescale the Higgs field by multiplication by scalars. And so that gives you some kind of a natural C star action on the left-hand side. And then the fixed points of that C star action are these graded Higgs bundles. And that corresponds to the fact that things coming from geometry should be fixed under the C star action. So those, some kind of a philosophical statement, but I think that is an explanation for where the Higgs field is coming from. Okay, great. So that's the classical story. And what I would like to do in this talk is explain a p-adic counterpart to at least some aspects of this picture. I will not say anything about these conditions because they're currently still mysterious. Are there any questions? Okay, so if not, let's keep going. Let me try to see if I can do this in a slightly better way. Seamless might be better. Yeah, good. So let me, if I want to do the p-adic version of the story, I need to tell you at least a little bit of background in p-adic Hodge theory. And I will try to keep things as simple as possible, but we'll see how far we get. And so the formulation of p-adic Hodge theory I'm discussing right now is the one that originated in the work of Faltings, and then was reimagined by Schulze using perfectoids. I will try to not sort of pass through the perfectoid world unless it is necessary, but at some point it will be necessary. So C is going to be my ground field, and I will take my ground field to be a perfectoid field. Okay, this word appearance of the word perfectoid is not supposed to be like the hard part. Okay, you can imagine C as the algebraic closure of QP completed. X over C is a smooth rigid analytic space. You can take it to be an algebraic variety if you wish, but at some point in this talk, we will run into rigid spaces that cannot be thought about, but where you lose some information if you think about the algebraic counterparts. And any rigid space has an associated etale site. And so just to make things precise, I'm using the etale site in the sense of Huber. It won't matter that much which version of, well, I think it doesn't matter which version of the etale site you use, but let's just use Huber's language of adic spaces for definiteness. So all the action is going to take place on this site. And there are some interesting sheaves on this site that that organize p-adic Hodge theory. And so maybe the first one to mention is the structure sheaf, OX. This is just a sheaf of rigid analytic functions. And there's not too many surprises in working with this object. It works like it does in complex analytic geometry. So for example, if X was proper, and if X was the analytification of a proper algebraic variety, then the cohomology of the sheaf would be what you would expect it to be from algebraic geometry, the cohomology of the structure sheaf. But this is a sheaf of QP algebras. P is inverted in the sheaf. Inside of it, there's a very interesting subsheaf, which is the sheaf of bounded functions. More precisely, the sheaf of functions bounded by 1 at every point. And so let me informally write it like so. So it's sections are sections of OX with the property that their absolute value at every point is less than or equal to 1. And unlike unlike this sheaf, which was a sheaf of QP algebras, this guy over here is only a sheaf of ZP algebras, because P has this property that the absolute value at every point is less than or equal to 1, but 1 over P does not. And so the fact that this is an integral sheaf gives it most of its power. And so let me tell you why I'm emphasizing working with this sheaf. So what are some of its features? Okay, so maybe the first thing that's worth saying is after you invert P, you recover the old story. So if you take OX plus, invert P, you just get OX. Basically because on a quasi-compact open subset, any function can be multiplied by a sufficiently large power of P to make it uniformly bounded by 1 everywhere. And so what this means, let me just rewrite what I was saying earlier. This guy is the same as R gamma of OX plus with P inverted is the same as R gamma of OX. And this, I will just say, works as expected. And let me not try to make it too precise right now. I hope it's clear what I mean. But so the interesting thing starts happening when you contemplate what happens when you don't invert P. And so let me call this feature the etale feature of the sheaf. So for this, let me assume X is proper, and I'll comment on where the assumption gets used. X over C is proper. Then for any integer n bigger than or equal to 1, we have a natural map, which goes like so. So I can look at the etale cohomology with constant coefficients, z mod p to the n, and this maps to the etale cohomology with coefficients in OX plus mod p to the n, just because the OX plus mod p to the n is a sheaf of z mod p to the n algebras. So there's a map of sheaves from here to here, and therefore there's a map on cohomology. But the target is naturally linear. This is linear over the ground field, or over the ground ring, which is the ring of integers of C, OC. And so what this means is that you can extend scalars from z mod p to the n to OC mod p to the n and still get a map. And now the surprising thing is that this map is actually an almost isomorphism. So this map is an almost isomorphism. And both sides are finally generated. So I'll just say both sides are finiteness properties. What I technically mean is that both sides are almost finitely generated. But if you're imagining you're coming from algebraic geometry, then this is just then etale cohomology is just where you think it is, and so there's no surprises. And so I want to stress that this is so maybe first of all, let me just say a word about almost, which in this context, which is what Faltings discovered, is you can declare a map to be an almost isomorphism if its cone is almost 0, and almost 0 means annihilated by not just P, but actually every small power of P. And it turns out that if you require this kind of stronger annihilator assumption, it becomes very close to being 0, and so you can, for many purposes, you can treat these maps as if they were isomorphisms. And so, for example, whenever you have a sequence of almost isomorphisms like this, you can pass to the limit and invert P, and you still get an isomorphism. Well, if you pass to the limit, you get an almost isomorphism, and then when you invert P, you get an isomorphism. So here's one concrete consequence of this, which is if you look at the etale cohomology with QP coefficients, and you tensor it over QP with the ground field C, it's actually isomorphic to the analogous thing on the right-hand side, which I will just write out. So it's R gamma of X OX plus, p-adically completed, that's what the hat means, and invert P. Okay, so this OX plus is now, what have we learned so far? The first point was that when you invert P, you end up getting coherent cohomology. Second point is that when you P complete first and then invert P, you get etale cohomology. This is still not quite giving you Hodge theory, although it's giving you a connection between coherent cohomology and etale cohomology. It's not, you don't see differential forms if I just state it like this. And so for this, I have a third feature I want to tell you, which is the following. So I'll call this the Hodge state feature. And so let me, for this, make a assumption, which just to simplify my life, which is X is quasi-compact and quasi-separated. For example, it could be proper, but it's a much, much weaker condition. So what the theorem is going to say is that this gadget that's showing up over here can actually be completely described in terms of differential forms. So then there exists a filtration on R gamma X OX plus completed P inverted, whose graded pieces are given by Hodge cohomology. So more precisely, with ger I given by R gamma of X with coefficients in omega I twisted by minus I, shifted by minus I. And so up to having this filtration around, this gadget over here is completely controlled by differential forms. And so if you combine 2 and 3, you get something that now smells much more like usual Hodge theory. And so just to comment on this filtration, let me make one small comment about it, which is the following. So there's a natural way to split it. So moreover, if X is lifted to the analog of the second of width vectors in this setting. So if X is lifted to what I will call B2C, which is a canonical square zero extension of C, of my ground field C that was written down by Fontaine. It's an extension of C by a copy of C twisted by 1. But it's a non-trivial extension if you're thinking about it as like topological objects, or even as Galois covariant objects. So there's this non-trivial square zero extension, and then the statement is that if X comes equipped with a lift to this non-trivial square zero extension, then the above filtration naturally splits. And naturally here means naturally in the lift. This is a similar assumption to what one encounters in the Delaunay-Loci theorem in Kersig P. Duran theory, and one can put them on the same footing. For now, I just want to say that this assumption is always satisfied if X is defined over a discretely valued field. So if you come from something like QP or a finite extension of QP, there's a canonical lift of X to B2 of C, and so therefore there's a canonical isomorphism of this guy with the direct sum of these guys. In general, if X is proper, it turns out there's always a lift by the result of Conrad and Gaber, but there could be many lifts. So there's definitely a choice.
I'm sorry, Bhargav, could you go back a second? This X, did it come with an integral model or not? I forgot. It just,
No.
or just, no, okay. Very interesting, okay.
Right, I mean, you can try to, if you sort of ignore the etale side here and think about just the analytic side, I could still say define analogous sheaves. And then you could think of this sheaf as essentially the structure sheaf of the Riemann-Zariski space of any formal model. So you take the inverse limit of all formal models, and there's a natural sort of integral sheaf there. And that's what this would be if I was doing the analytic topology.
Thank you.
Other questions? Okay, so the goal of this talk is essentially to do a nonlinear version of 2 and 3. So I have this object over here, R gamma XOX plus with P inverted. Item 2 is saying that it's completely related to it is essentially the same information as etale cohomology. And item 3 is saying it's up to this filtration issue is also the same information as Hodge cohomology. And so you see some kind of Hodge theory happening in this p-adic world through this combination. And today we want to do something analogous with nonlinear coefficients. So today you want a nonlinear version of this. in the same way that the Correlate-Simpson theorem was a nonlinear version of a classical Hodge theory. And so there's sort of there's an obvious thing you can try doing once you sort of know about this sheaf and what you can do with it. And so let me just draw the picture and see, reformulate what this goal actually is. So you can consider the category of local systems on X etale with coefficients in OC mod p to the n. So I'm just using OC instead of Z mod p to the n over here because in the etale comparison up here, sort of you could have just pulled this OC mod p to the n into the inside by the projection formula. So this is sort of the more natural object that comes up in this world. And so we can contemplate local systems with coefficients in this sheaf of rings. This functor of tensoring over OC mod p to the n with OX plus mod p to the n that was showing up earlier, it gives you a very well-behaved functor to, well, it's local systems, but now I want to think of it as having coefficients in some kind of sheaf of functions. So let me call it vector bundles. So it's vector bundles on X etale with coefficients in OX plus mod p to the n. Okay, and then let me just write in red font that this functor over here is essentially by this. Sorry, I didn't give this a name earlier. This theorem is called the primitive comparison theorem, and so it's not so hard to go from the primitive comparison theorem to an analogous statement where I twist by a local system on the Z mod p to the n part. And so if you do that, what you learned is that this functor over here is almost fully faithful. So we already have a way of turning local systems into things that look more coherent, coming from the way p-adic Hodge theory is set up in this approach. But we want to do something with rational coefficients. So let me first pass to the inverse limit over n on both sides. Now, the left-hand side, essentially by definition, is local systems on X with coefficients in OC. But since my coefficient sheaf now involves a topology, it's more correct to write pro-étale over here instead of étale, because the local systems will not themselves be trivialized by a particular finite cover. You'll need a compatible sequence of finite covers. Okay, and analogously on this side, what you get is vector bundles on X pro-étale with coefficients in OX plus hat. This is just notation, if you like. This is literally the inverse limit of these categories. Okay, so this is the integral coefficients at play, but we want a rational theory. So we want to invert P. And so let me do that. Let me invert P. But usually what happens when you invert P in some functor like this is that you lose descent. Things cannot be constructed locally, and so you have to turn that back on. So you invert P plus étale sheafify. And what you get is exactly the category of pro-étale local systems with C coefficients. So this is the analog of complex local systems on a compact complex manifold. So this is C local systems on a smooth rigid space over C. And you can do exactly the same thing over here. Invert P plus étale sheafify. And the result, I'm just going to call vector bundles on X pro-étale with coefficients in OX hat. This is just notation. If you know what this notation means, it's also a theorem that disagrees with what you get by inverting P and étale sheafifying this object. But if you don't know what it means, just take this as a definition.
I'm sorry, Bhargav, can I interrupt you yet again?
Yep.
Why do you want a rational theory? Why don't you just work with almost fully faithful or almost equivalent and stuff like that, and keep the integral structure? Is that no good?
You can try, but like first of all, my X didn't come with an integral model, and so you would have to pick an integral model. And
Okay.
it turns out that, as I'll try to explain, like even if you picked an integral model, you'll have to keep changing it depending on which local systems you want to work with. So depending on how small your local system is, you'll have to enlarge your integral model. And so it's cleaner to obtain. If you want a cleaner statement, I think it's better to invert P.
Okay.
To prove things, of course, you do work integrally.
Okay.
And so I just wanted to make one point of contact with the perfectoid theory, which is this category that's appearing over here. I mean, I defined it by an abstract procedure, which is I took the inverse limit of OX plus mod p to the n vector bundles on the etale side, and I did some formal operations to it. But it can also, it really has a quasi-coherent nature. So it can be described as follows. It's the inverse limit of just the category of vector bundles over R, where the inverse limit ranges over all maps from perfectoid spaces to X. So it's the same as specifying a vector bundle over any perfectoid space mapping to X. It's equivalent data. And this perspective is very useful in proving theorems about this category. I will not show up so much in this talk today, but I feel like I have to at least mention that this is how we actually work with it. And so, sorry?
So can I ask something here? So if you start with the OC local system over pro-étale side, are you trying to say like if you invert by P and it's not always a local system?
No, I'm not saying that. That part is fine. What could happen is that you could have two you could have C local systems that don't admit an OC lattice, but only etale locally they would admit an OC lattice. I'll try to give an example of this later. It already happens over P1. So I want to include these examples.
Okay, thank you.
Right, and so we already, so this diagram that I've drawn over here already gives you a procedure for turning complex local systems or C local systems on X into something that feels kind of coherent. And so the goal of this talk essentially is to describe what this category has to do with Higgs bundles. So goal is to describe vector bundles on X pro-étale with coefficients in OX hat as twisted Higgs bundles. This is more or less what I promised in the abstract, and now I can try to make it more precise. Maybe I should just make a couple of comments before I actually start writing down formal statements, which is, first of all, the fact that there's a twist that shows up in relating this category to Higgs bundles shouldn't be surprising. If you think back to what Hodge theory tells us, it tells us that something that's essentially the same as etale cohomology can be described in terms of differential forms only up to a filtration. And splitting that filtration requires some additional choices. And so you should expect some twists to show up when you try to understand the nonlinear version of that question as well. The second comment is, so one of the key ideas, for me at least, in this project is the idea of working locally on the cotangent bundle rather than working locally on X. These twists are going to happen locally on T star X rather than on X. And this idea definitely came from our learning seminar we had on Ben Hoyer's work here last semester. And so I can try to explain that a bit more when I write down his theorems. And maybe the third thing to say is that this picture was also inspired by the Ogus-Vologodsky theory, which builds on Bezrukovnikov's observation that for smooth variety in characteristic P, the algebra of differential operators is Azumaya over the cotangent bundle. And so you can think about D modules in characteristic P as essentially some kind of twisted sheaves on the cotangent bundle. And what I'm describing here is a characteristic zero analog of that. And there's also a version of the story for formal schemes which relates to both those things, which I can talk about at the end if there's some time. Okay, so now let's get down to business now that I've actually stated what I want to do. So what's the main theorem? Actually, I need some setup for that. So from now on, C is always going to be a perfectoid field. Although you can take it to be perfectoid space if you wish. And X over C is a smooth rigid space. There's no quasi-compactness or properness assumption. And it's actually important for the way we set things up because our proofs are going to be all local on X. And so if you were assuming X was proper, then this would be quite awkward. And so let me recall two kind of basic facts in algebraic geometry before formulating the theorem. And these are just sort of standard things, but it's just worth having them on the blackboard, quote unquote, before writing things down. So first is how to think about Higgs bundles. in terms of things on the cotangent bundle, and it's extremely simple. So if I give you, the category of Higgs bundles on X, sorry, Higgs can be identified as just a certain class of coherent sheaves on the cotangent bundle. Namely, it's those coherent sheaves on T star X, which have two properties. One is that their support is finite over X via the projection. And the second is that when you think about them as sheaves on X via push forward, they're locally free. And so let me just draw a picture of what's going on. Here's the cotangent bundle. Here's the projection to X. Whenever you have such a gadget E, it has some support, which looks like this. Let's say Z, the support of E. And so the assumption is that this support is finite over X. So the picture is not bad approximation of what's going on. And moreover, when you think about E as living on this support, its push forward down to X becomes finite locally free. And the conversion between this perspective and this perspective is just the obvious one. Namely, if I give you such a thing, you can think about it as a sheaf on X together with an action of sim star of the dual of the cotangent bundle. So with an action of sim star of the tangent bundle, and that's exactly what a Higgs bundle is. So this is essentially tautological, but it's extremely useful psychologically to localize on this space T star X. And the second point is something about twisted sheaves, just some generality on twisted sheaves, and it's the following. So if I give you a GM gerb, so a GM gerb, if you like, is a BGM torsor. So essentially, there's a simply transitive action of BGM on P, and the quotient by that action is the base Y. So if I give you a GM gerb, then its category, it's an algebraic stack of some sort over Y. And so there's a reasonable theory of coherent sheaves. And the statement is that that category has a natural Z grading. Co of P has a natural Z grading. And this is not very mysterious. If you're thinking of P as having an action of BGM, that means that each point, and you have a coherent sheaf on P, then when you take the fiber at a point, you get a representation of GM, and I'm decomposing it into its eigenspaces. And so this is where the Z grading comes from. And the example to keep in mind of this is the following. So if I give you A as an Azumaya algebra over X, so a twisted form of the matrix algebra over Y, sorry. Then there is a natural GM gerb you can write down associated to this, which is the GM gerb of splittings of A. And the way this gerb is designed, it has the feature that if you look at coherent sheaves on the gerb, and then you look at the degree I part, so with respect to this grading, then you get exactly A tensor I modules in coherent sheaves on Y.
What if I is negative?
It's the dual to tensor power I.
Dual means opposite.
Right, the inverse in the Bhargav.
But in down to earth terms, this means that you replace. So for I equals -1, you consider right A modules instead of
right. Yeah, thank you. So one of the issues is going to be that Azumaya algebra is actually, like, in algebraic geometry, they have finite rank by definition. And we're going to be in a setting where things don't have finite rank, and it messes with my head. Okay, so these are the two facts I wanted to recall, and now I can state the theorem. And in some sense, I've already given it away, so it's not going to be surprising. So the statement is that there is a natural GM gerb on the cotangent bundle of my smooth rigid space. We call it the Simpson gerb, P, which lives over T star X. And really, there was one thing I should have emphasized right from the start, is that the cotangent bundle in p-adic Hodge theory always naturally comes with a twist of -1 in various calculations. And so really this lives over T star X twisted by -1. You can ignore this if you're working over an algebraically closed field like I am, or at least over a perfectoid field, and you don't care about the Galois actions, but it's more canonical to keep it there. So I will try to keep it there. So there's a natural GM gerb P over this cotangent bundle and a natural equivalence between twisted Higgs bundles twisted by this gerb and the category I was interested in. So I was interested in this category of pro-étale vector bundles with coefficients in O hat. And this identifies with Higgs bundles on X, but twisted by this gerb. And so what do I mean by this? I mean those coherent sheaves on the gerb, which have degree 1, in the sense I was just discussing, and they have the same support features that showed up earlier. So the support of E is finite over X, and E is locally free over X. So let me just go back to this picture because it's going to be the same picture now. Now imagine that you had some GM gerb that lives over the cotangent bundle. So physically, the space looks more or less the same, and then there's some twisting going on, but sheaves of support still on the underlying space. And so the conditions I'm imposing on my twisted sheaf are exactly those that showed up in my definition of Higgs bundles as via coherent sheaves on T star X. And so this is the theorem. And the rest of the talk, I think, will be a whole sequence of remarks about this gerb and a construction of it. But let me just say what the upshot is going to be right off the bat. So the upshot is you do not get an equivalence with Higgs bundles on the nose. Rather, you get an equivalence with this notion of twisted Higgs bundles. And then each time you can trivialize the twist, you get an honest equivalence with Higgs bundles. So the upshot is to get honest Simpson correspondences. You need to trivialize the gerb over whatever, well, ideally over the whole space, but it turns out that this is basically never possible. Instead, you can trivialize it on various chunks or various subsets of the cotangent bundle. And once you trivialize it on that subset, you get an equivalence for Higgs bundles satisfying some conditions with pro-étale vector bundles satisfying the same conditions. So you have to trivialize P over suitable loci in my cotangent bundle.
Bhargav, another question, if you don't mind. What about other degrees?
What about other degrees?
Right. So you have degree Higgs bundles of degree 1 correspond to vector bundles. What about our other degrees, like even degree 0? Maybe that's.
Well, degree 0 is always the thing you're taking the gerb over. So it will just be coherent sheaves on it will be usual Higgs bundles.
Okay, and how about higher degrees? Or do you have any idea what these correspond to? I'm talking what do they correspond to on the left side, not on the right side?
Right. So I haven't sorted this out completely. My suspicion is that they're actually all isomorphic to each other.
Okay.
Because this gerb has infinite order. In fact, really, like, yeah, the gerb is infinite order. And in fact, sort of the class of the gerb spans a copy of the complex numbers inside the Brar group. And so my feeling is that they're all identified with each other, but that's just a guess. I haven't actually sorted this out.
Okay.
I have a minor question.
Mhm.
You denote your equivalence by capital S. Does this letter stands for Simpson?
Yes.
Yes, that too.
I mean, I was just imitating what other people in the subject do.
Yes, this is, but anyway, it helps just psychologically to know that as the meaning of the letters.
Yeah, it's the Simpson functor.
Yes, of course you can say that it's correlates Simpson, but Faltings called this Simpson.
Right.
So we have to.
I guess this is a talk at Chicago, so I should really call it correlate Simpson. I'm sorry. Subject.
Yes, also different Cartier, right? So Cartier Simpson, call it Simpson.
Yeah. Okay, so let me just call it S to risk offending fewer people. I apologize. Okay, remarks. So there are a bunch of things to say. First of all, I didn't emphasize it earlier, but the classical correlate Simpson equivalence was a tensor equivalence. It transformed tensor products of local systems into tensor products of Higgs bundles. And you can ask a similar question here, except a priori that question doesn't make any sense because there's no tensor product on this side. If you did the natural tensor product on twisted sheaves on P, it would move the degree around. Degree 1 will go to degree 2 if you tensor 2 degree 1 things together and so on. But there's a second tensor product, which comes by thinking about T star X as a group over X. So T star X is a group over X, and so there's a addition law on T star X, which gives you a convolution product on T star X. And it turns out that this passes to the twist as well. And so let me say it more formally. So more formally, this gerb P is naturally a multiplicative gerb. And so one way to say this is the following. So you have this cotangent bundle with a twist. You have its classifying map of the gerb. So GM torsors are classified by BGM, and GM gerbs are classified by B squared GM. So you end up going into B squared GM. And the statement, and I'm imagining everything is happening in the world of sheaves over X. And the statement that P is multiplicative is the statement that this map is naturally an E infinity map. Which just means that it's compatible with the sort of addition law in the best possible sense. In particular, it tells you that this gerb is trivial over the zero section. So this has some consequences. A is that P is not, well, it's trivialized, it's naturally trivial over the zero section. And so then this theorem has a companion theorem, which is a comparison of cohomology. So I'll call it theorem prime, which is that for every vector bundle on the pro-étale site, the cohomology of that vector bundle, which we saw earlier was a generalization of etale cohomology when, in the case where E was the trivial vector bundle, is naturally identified with R-harms on this twisted sheaf category. So R-harms over P from the structure sheaf of the zero section. So zero lower star of the structure sheaf of O of X. Sorry. I hope it's clear what I mean. To the Simpson partner P. So what am I saying here is that because the gerb is trivial over the origin with the zero section, the structure sheaf of the zero section can be naturally thought of as a twisted sheaf by putting it in degree 1 because the gerb was trivial there. So after you put it in degree 1, it makes sense to contemplate this kind of R-harm, and it will produce some version of the Higgs cohomology of the Higgs bundle. And we're saying that the Higgs cohomology of the associated Higgs bundle is the same as the pro-étale cohomology of the local system you started with. In fact, so this is slight improvement over what I said in New York. So in fact, everything I've said so far works for perfect complexes. So I can just replace the word vector bundle with perfect complexes everywhere. And the statements are still true. In particular, we get some kind of a Simpson equivalence for perfect complexes, and that includes within it this statement about comparison of cohomology. Okay, and then the second remark is the one I started this point with, which is you get a convolution product on P, and so there's a natural symmetric monoidal structure on twisted sheaves. So these twisted Higgs sheaves have a natural tensor structure. Which I will just say it comes from convolution. And the functor S is a tensor equivalence. So you do get a statement about symmetric monoidal structures as well. You just have to observe a little bit more. Okay. So that was the first remark. The second remark is something about the class of this gerb. So the class of this gerb, or I just called it P, I guess. Okay. So P, it's an element of H2 of T star X minus 1 with coefficients in GM, everything happening in the etale topology. And you can ask, what do you know about this class? And so it turns out it has infinite order. As long as X is not a point. But if you restrict, so the cotangent bundle is if you think about it as a rigid space, it's some non-quasi-compact space, because in the fiber direction, you have this kind of big vector space. But if you restrict this gerb to a quasi-compact locus inside the cotangent bundle, it actually has finite order. And so this will maybe make a little more sense after I state the next remark, which gives a reduction of the structure group of the gerb. But this already tells you that this, even if X was projective algebraic variety, if X was P1, this gerb does not come from algebraic geometry, because GM gerbs on smooth varieties have finite order, but this one does not. And so it's really an analytic object. The other remark that's maybe worth making is that if you were doing algebraic geometry, you would expect functors like the Brouwer group to be homotopy invariant, A1 homotopy invariant. So if you had like a Brouwer class on a vector space, you would expect that it's completely determined by its restriction to the zero section. But I just told you that the gerb was trivial over the zero section and is non-trivial globally. And so therefore, this also gives you an example showing that A1 homotopy invariance is not true if you work in this in the rigid analytic world with the rigid analytic Brouwer group. But it's not some pathological thing. It's actually a highly interesting object. Okay. Now let me come back to this lift. Earlier I said that if you wanted to split the Hodge state filtration on etale cohomology, you needed a lift of X to b to rom mod T squared. And I want to explain what that lift tells you in terms of this gerb. So say X has been lifted to some X over the square zero extension that showed up earlier, B2C. And so given this lift, you get a reduction of structure group to mu p infinity. So more precisely, there exists a natural factorization compatible with all the structures that you would hope for, like so. So concretely, the cohomology class in H2 GM is actually coming from a cohomology class in H2 mu p infinity. But this is the canonical map, and this factorization over here depends on the lift. And so again, this is a cohomology class with coefficients in a torsion group. If you were doing algebraic geometry, you would expect that such cohomology classes are torsion. But what's going on over here is that this is not quasi-compact. And so on some non-quasi-compact space, cohomology with coefficients in a torsion group need not be torsion, and this is an example. But this has some positive consequences. So the key point is that this group that's showing up over here is etale. It's a discrete group. It's just, well, I didn't assume C had roots of unity, but if C had all roots of unity in it, then it would literally be just the constant group Q mod Z, or QP mod ZP. And so etale cohomology with constant coefficients is a topological invariant. It doesn't sort of see nilpotence. And so a consequence of this is that the gerb is actually trivialized in a formal neighborhood of the zero section. And so what does this mean concretely in terms of sheaves? If you go back to this picture I had.
Sorry, is it naturally trivialized if you have a lift over B2?
Yes, yes. This is trivialized using the lift. Is that, sorry, is that okay? It's natural in the lift. Wait, can you hear me?
Yep, it's okay.
It's okay?
Yeah, I think so. It's a little slow, but yeah.
Sorry, okay. Should I continue or?
Yep.
Okay, thank you. Right, so this is naturally trivialized on the zero along in a formal neighborhood of the zero section using this lift of X. And so what that tells you is, so let me, well, okay, let me just draw in this picture. I'll just draw the zero section because I didn't draw it earlier. So if the zero section somewhere over here, let's say, what this is saying is that the gerb is naturally trivial in a formal neighborhood of the zero section, and you can even make it an analytic neighborhood if you want. And so if you're working with those Higgs bundles that are supported in this region, in the locus where the gerb is trivial, then the twist disappears and you are just talking about usual Higgs bundles. So on the formal completion, you're literally just talking about nilpotent Higgs bundles. And so you can use this to show to obtain a nilpotent Simpson correspondence. So corollary is that you get a nilpotent Simpson correspondence. And so this is something I think a lot of people have already understood before. I was just trying to explain how to see it in terms of the gerb. I think it goes back at least to the work of Suji. There was a paper on the archive about a month ago giving a modern perspective on this. And there are probably other works that I'm not aware of, but I just want to make it clear that this is not new.
I have another question, which is probably nonsense, but I'd like to ask it anyway. So we're sort of in characteristic zero here in some sense, but since things are sort of not quasi-compact and there's some limits involved, I'm not completely sure, but is there some notion of taking the divided power neighborhood of the zero section instead of the formal completion that's a little different because of this business? And if you'd have some trivialization which didn't depend on the lift on such a divided power neighborhood of the zero section. Does that make sense at all?
It makes sense, but first of all, I don't think, I think the trivialization will depend on the choice of the lift already on the formal neighborhood.
Yes.
And therefore on any honest neighborhood. Like the divided power neighborhood would actually be an honest neighborhood, so it would contain the formal neighborhood. And
no,
so
the other way around. It should be the other way around. The divided power neighborhood usually is contained in the formal neighborhood.
No, but that's in characteristic P. In characteristic zero, having divided powers is just a condition that something is divisible by a slight amount of.
Well, that's what I was wondering, because things aren't quasi-compact. I thought there might be some difference here, but you take you take the divided power completion, the divided power envelope, and then you p-adically complete that. That's contained inside the formal neighborhood. So it's
right, but when you invert P, that's much bigger than the formal.
That's what. Yeah, that was my
zero.
question. Yeah.
Yeah. So I think the formal completion zero is the smallest thing you can.
Okay.
You could possibly write down, and there are sort of bigger things you could write down. But I think the trivialization on anything like that will already on the square zero neighborhood.
Okay, that answers the question. Okay.
on the lift, yeah. Right, the other remark I wanted to make is about this map. So once I'm still in the setup where I have this lift to B2. And so we just explained why the class of the Simpson gerb actually factorizes this way. And this is a group homomorphism from T star X to mu p infinity. And I explained that it was trivial on the formal neighborhood just because there are no maps from the formal neighborhood into p squared mu p infinity. And so what that means is that this homomorphism from here to here actually factors over the quotient of the source by the formal completion. And concretely, what that buys you is a GM hat action. So you get a GM hat action on P, and therefore also on twisted Higgs sheaves, lifting the scalar multiplication action. On T star X. So I remind you that the scalar multiplication action on the cotangent bundle is the action that Simpson exploited extremely well to prove results on the fundamental group using the Simpson correspondence. In the p-adic setting, I'm not claiming you get a full GM action, but you could at least get an action of the infinitesimal version of GM, GM hat. I think Ben was explaining to me that you actually cannot do better than this. So like, I don't think you can get an action of a small enough honest open subgroup of GM on the gerb. So this is the best you can do, but it still has some consequences. And so one consequence of this is, depending on the data of a lift, I get the GM hat action on P. Now, I told you earlier that if X was defined over a discretely valued field, it has a canonical lift to B2. So that will produce a canonical GM hat action on P. Moreover, if my local system was also defined over a discretely valued field, then the corresponding pro-étale vector bundle will be equivariant for this action. And so, therefore, it will be equivariant for the corresponding twisted sheaf will be equivariant for the GM hat action, which means it has to be supported on a formal neighborhood of the zero section, which means it has to be a nilpotent Higgs bundle. And so this is something that was proven earlier by Liu and Zhu, and this is just a geometric way of saying essentially what they were doing, but let me just record it. So you get a nilpotent Higgs bundle for every local system defined over a discretely valued field. So if you have additional Galois symmetries, then your Higgs field is always nilpotent, and this is one explanation of it. As I said, this was, I think, first written down by Liu and Zhu. I'm just trying to say what the GM hat action is doing for you.
Bhargav, can I ask something?
Mm-hmm.
So when I'm talking about this Nilpotent Simpson correspondence, so what is it? So are you trying to say there's a subcategory of a pro-étale vector bundle corresponding to nilpotent ones?
Right. You could, so I didn't want to assume too much background, but there is this canonical Higgs field on pro-étale vector bundles. I mean, if you use this equivalence, if I use this equivalence, I'm just observing that on the right-hand side, there's an action of Higgs fields on objects of this category, because Higgs fields are where you get in the degree 0 part of the category, and you can tensor them with stuff in the degree 1 part of the category, and you get something in the degree 1 part of the category. So you can use that observation to see that there's a natural action of Higgs fields on this side, and on this side. So any pro-étale vector bundle has its own intrinsic Higgs field. This was first, so I believe this first appeared in the work of Louis Pan, and then really in Juan Esteban Rodriguez Camargo. And so I'm saying that if you restrict to the nilpotent guys on this side, you can ignore the twist, and the corresponding thing on this side are pro-étale vector bundles whose canonical Higgs field is nilpotent.
But do you expect if there's any more intrinsic way of describing this subcategory, or some other way of thinking about that?
Well, it's pretty intrinsic. I think the canonical Higgs field is canonical.
Okay, yeah, okay. So you have to go through to look at the canonical Higgs structures in order to talk about this subcategory. Oh.
at least that's the only answer I can think of right now.
Ah. Okay, thank you.
Other questions? So I actually wanted to do an example at this point before explaining the relation to the work of Faltings and Hoyer. And so the example.
So it's more or less time for the break. So if you wish, if the example is not too long, and if you prefer to give an example after the break, it's okay. But at some point we need a break.
We can take a break now. I'll just do the example after the break.
Can you tell us?
Okay, let me continue. So I wanted to give an example of this correspondence. And one, because the example is fun, but two, because it also illustrates that there's this highly interesting question of what is the essential image of honest local systems under this correspondence. So I recall what we have done so far is we translated from local systems, we gave a fully faithful functor from local systems to pro-étale vector bundles. Well, it was fully faithful on the integral objects, but okay. And then we explained what pro-étale vector bundles were in terms of Higgs data. But it's natural to want to know what the honest local systems are. And I just want to point out that this question can be quite subtle. And so I want to explain the following example. So let's say X is P1. And L is a rank 2 QP local system on P1 with monodromy group SL2QP. So this is a genuinely rigid analytic object. It doesn't have a stable ZP lattice. All the ZP local systems on P1 are trivial. But this is a very interesting one. It's associated to the Gross-Hopkins period map. And I don't want to describe it more than what I've written already, but maybe I should just say the key feature for the purposes of actually understanding the calculation is that etale locally on P1, it's the Gauss-Manin local system associated to a versal family of elliptic curves. And so just using that, you can verify the assertions I'm making. And the assertion is going to be the following. So I have this pro-étale vector bundle, L tensor OX hat, tensored over, I guess, QP. I can apply my functor to it, and I get a twisted Higgs bundle. Now this local system was actually defined over a discretely valued field. And so I'm in the
Did you repeat what you said about this versal family?
Sorry.
Repeat what you said about the versal family.
So the assertion was that there's an etale cover of P1 where the pullback of the local system is the H1 for a versal family of elliptic curves over that etale cover. It's just that the etale cover doesn't descend to P1.
Okay.
Right. So this local system has Galois symmetries. It's defined over a discretely valued field. And so I'm actually in the setting of a nilpotent Simpson correspondence. And so I can basically ignore my twist and I get an honest Higgs bundle with a nilpotent Higgs field. And I just want to tell you what it is because it's a very classical object. So it's E comma theta, where E is the rank 2 vector bundle on P1 given by OX of 1 plus OX of -1. And theta is the interesting Higgs field on this. So there's only one interesting one. I can take E and I can project down to the second factor. I can identify the second factor with the first factor tensored the canonical of P1. And this includes into E tensor omega 1. And so it's this rank 1 nilpotent operator which projects the second factor onto the first factor as my Higgs field. But the sort of interesting feature here is that the first factor, OX of 1, is annihilated by the Higgs field because it was annihilated by the first step. And so it's a Higgs subbundle, and it manifestly has degree bigger than the degree of the rank 2 bundle. And so observe that it's not stable.
Mhm.
It's not semi-stable even. And so in the classical complex story, local systems corresponded to semi-stable Higgs bundles with vanishing Chern classes. But here's an example where an interesting QP local system corresponds to something not semi-stable. And so whatever the essential image of this functor is, if you want to use it to describe all QP local systems, you're going to have to reimagine what the Simpson correspondence would look like, and which is also why I have nothing positive to say about that question. But I thought this was a fun example. Okay, any questions about the example? Okay, if not, so let me continue with my sequence of remarks. So what have I said so far? Let's just do a quick recap.
Just a moment. So is there an elementary way to construct this E or maybe another E where the monodromy doesn't have a let in invariant lattice?
Sorry, I think my internet.
If you don't, if an elementary description doesn't come to your mind, it's okay. But just there is.
I don't know one off the top of my head.
Mhm.
Okay, so quick recap. I've described. I've told you what the theorem is. I've told you that the gerb is multiplicative, and then I told you a little bit about how to trivialize it. Namely, I told you how to trivialize it on the formal neighborhood, and we can use that to get some kind of nice consequences. Let me now explain this work of Hoyer, which was inspired by earlier work of Faltings in this language. It sort of gives a much larger trivialization of the gerb. So now we need more assumptions. So say X over C is proper. Until now, I didn't need properness, but now we do. And okay, and C has to be algebraically closed now. So far C was just perfectoid, but now we actually need more than that. Let's make two more choices. So choose this lift to B2C. As I said before, this always exists by work of Conrad and Gabor, and maybe there's a canonical one in arithmetic situations, but anyways, let's make a choice. And let's also choose an exponential function. So an exponential function is a homomorphism from C to 1 plus the maximal ideal of OC, which splits the logarithm. So the logarithm is a completely canonical map that goes from here to here, 1 plus MOC to C. It doesn't have a preferred splitting. It has a preferred splitting on a small chunk of C. Like if you work, something that's divisible by enough powers of P, the exponential power series will make sense and it will give you a splitting. But if you haven't multiplied by enough powers of P, you don't know where to go. And so yeah, this involves a non-trivial choice, but it always exists, so we can choose it. And so we make this choice.
And the set of splittings is a torsor under exactly
homomorphisms from C into mu P infinity.
right. Yeah.
Which is some humongous thing. I mean, related to this is the fact that this, what I'm about to say is not going to base change well, because splittings, well, again, if you want to extend scalars, you will need more choices. And so here's the theorem. This is due to Faltings in dimension 1 and Hoyer in general. I forgot to look up the dates. I think this is Faltings' work is around 20 years ago, and Hoyer's work is about a year ago. And so this is not how they formulate the theorem, but I'm just reformulating it. With these choices, what they prove is that this gerb that I've been talking about, P to T star X minus 1. Let me say it carefully. Admits a trivialization. Not globally, because I told you earlier that the gerb is infinite order. So globally, it cannot be trivialized. But what they prove is that it can be trivialized on any subset of the cotangent bundle that appears as the support for a Higgs bundle. So it admits a trivialization over this locus, the Z inside the cotangent bundle, where the Z's range over closed subsets which are finite over X. Okay, so I'm just thinking of this as some kind of an end object. I don't want to, not making any assertions about some kind of a refined analytic structure on this. But it does admit such a trivialization, and it's even compatible with addition. So the left-hand side is stable under addition, and this is compatible with the group structure. And so you see, once you have such a trivialization over this locus, you can ignore the twist in some sense. Each time you meet a twisted Higgs bundle, you use this trivialization to undo the twist, you get an honest Higgs bundle. And so using this trivialization, you'll get an equivalence between pro-étale vector bundles and actual Higgs bundles. And the fact that this equivalence is compatible with the group structure, this trivialization is compatible with the group structure will tell you that the equivalence you produce this way is a tensor equivalence. So that's the good news. The bad news is that this equivalence really depends on choices, and more so than the two that are written on the screen. So you definitely need this lift x to b2c. You definitely need the exponential, but there's a third layer of choices that goes into the proof, which involves essentially choosing base points on each of these z's in some fashion. I don't want to get into, but the consequence of that is that this equivalence is not an equivalence of functors. And so actually, let me write the equivalence first before I talk about it. So it admits a trivialization compatible with group structures, and therefore you get an equivalence, get a tensor equivalence between pro-étale vector bundles and usual Higgs bundles. Well, twisted by -1, as always. And so the comment I was making is that the equivalence you get this way, which depends on this trivialization, depends on all of these additional choices. And so it's not functorial in X under pullback. But that's the price you pay for getting such a clean statement. And so let me.
Did you say anything about how you choose compatible base points under all these z's? Each other?
You just have to make infinitely many choices or something like that.
Yeah, so essentially, like, I mean, I think one way to think about it is if you just think about what it means to trivialize a GM gerb over this, the space of trivializations would be a torsor for sort of the space of trivializations over each z, the torsor for the Picard stack of z. And essentially, the base points come in and going from the Picard stack to the Picard variety. I don't think I can say anything more than that, but that's at least my understanding of the choices are coming in. And so just I just wanted to make two warnings about this. One of which I already said, and the other already made by Faltings. So the first one is that the equivalence above is not natural in the obvious choices, namely the choice of the lift and the choice of the exponential function. There's a third layer of choices coming from base points. And the second warning, which was already made by Faltings in his initial paper on the subject, is that some subtlety has to come in because there's no Galois equivariant equivalence between the two sides. There is no GK equivariant. If you have already descended to a discretely valued field, you might ask for a Galois equivariant Simpson correspondence, and there just isn't one. So there's no GK equivariant equivalence between even the rank 1 objects. So pick of X pro-étale and pick of Higgs. So Higgs line bundles. He has a concrete obstruction that you want a certain exact sequence to be split. It splits as a sequence of abelian groups, but not as a sequence of Galois modules. So this is, in some sense, the best you can do if you want to ignore the twist. Okay, right. So this is the it was on our seminar on Hoyer's work, which was phrased in a different language, but these Z's were showing up a lot, and that's what led to the discovery that I'm reporting on today. So I promise I mention this later, and this is the point. Okay, I want to make one further remark about this and then talk about the construction of the gerb. So the remark concerns the characteristic P story. And I don't want to say too much about it because it would require setting up too much notation, but I want to at least explain how what I'm talking about right now connects with the Ogus-Vologodsky story in characteristic P in very broad strokes. So say X over C now admits a smooth formal model.
From time to time, and my
right. So I wanted to talk about very briefly, just say what happens when you have integral models of things. And so say X over C admits a smooth formal model. Math frac X over OC. So I'm in the good reduction case. So then this Simpson gerb has an integral counterpart. So then there exists a GM gerb. Let me call it P of X. That lives over the cotangent bundle of X. There's a twist. Now the correct twist to use is the Breuer-Kissen twist, which is a renormalized version of the Tate twist. But it doesn't live over the full cotangent bundle. It only lives over the formal completion. And we can discuss how necessary this is afterwards if you want. There's a natural there's a GM gerb P of math frac X over this with the following features. So first thing you can do is you can sort of take the generic fiber of this gerb. And this essentially recovers the Simpson gerb to the extent that it can. So it recovers the Simpson gerb for the generic fiber. Let me just denote that as P of X, except it cannot, because I mean, this guy over here lives on the generic fiber of this completed cotangent bundle, which is inside the cotangent bundle of the generic fiber. This is the radius less than 1 part. And so that's the best you can hope for, and that's what happens. Radius less than 1 ball inside P star X minus. So I think this also addresses maybe a question that came up earlier, which is if you use sort of integral models, you would only be able to discuss those Higgs bundles whose Higgs fields are small in the sense that they're supported inside this ball. If you wanted to talk about Higgs fields which are in a slightly larger ball, you would have to change your formal model. And then what happens when you go to the special fiber? So P of X, let me just call the residue field little k. This recovers this Ogus-Vologodsky or Bezrukovnikov's gerb. So it recovers the Azumaya algebra of differential operators, D of the special fiber. But again, the Azumaya algebra of differential operators lives on the full cotangent bundle, and we have to do this restriction to the formal completion. Okay, and so this is the sense in which this Simpson theory that I'm talking about in characteristic 0 relates to the corresponding theory in characteristic P. And there's this annoying hat that's showing up everywhere, like over here and over here, and this radius less than one part over here. So I believe one should be able to remove it using the work that using some ideas of Vadim Vologodsky, who's on the call. But I don't want to get into it right now. Okay, so that was the end of my sequence of remarks on this gerb, and my remaining time I'll talk about a couple of constructions of it. Are there any questions? Assuming the answer is no. So idea of construction. So I'll give one construction and then mention two more potential ways of doing it, one of which already came up in the discussion earlier. So let's say X over C is a smooth rigid space. Back in our original setting, we want to describe this gerb. And where does it come from? It's actually the most obvious thing you can imagine. You're trying to understand some kinds of quasi-coherent sheaves on the pro-étale side. And the sort of natural spectral way of doing something, understanding quasi-coherent sheaves on X, is to consider the moduli space of quasi-coherent sheaves of some sort, like maybe line bundles, and try to localize the picture there, and that's what we do. So in quotes, the definition of P is that it's the Picard stack of the pro-étale side over the étale side, or equivalently of the completed structure sheaf over the non-completed structure sheaf. And so to make this slightly more precise, let me tell you a key calculation, which was done by Ben. So we have this map nu from the pro-étale side to the étale side. And so there was this, earlier I mentioned that there was this Hodge-Tate filtration on the cohomology of O hat, and that can be rewritten as follows. So Ri nu lower star of this completed structure sheaf O hat is identified with omega I of X twisted by minus I. So this was a calculation of Schulze, or his version of some calculation of Faltings. And so what Ben Hoyer did, is he figured out what to do when you replace O hat with its units. And so I'm just gonna, let me call this 0, and then the relevant calculation for us is the following. So Ri nu lower star of O hat star, the units. What happens for I equals 0, you just get OX star. But for I bigger than 0, you just get whatever happens for the non-unit version. So omega I of minus I.
Now, I thought
Okay.
you have to choose some exponentials or something like that to make this isomorphism.
No. This is completely canonical.
Okay,
There's a logarithm involved, but the logarithm is well defined.
canonical.
Yeah.
Okay. Can you explain these calculations at all, or is it not time to do that?
I could try to explain how you get 1 from 0, but I don't think I can
Okay.
explain it right now. But let me do that at the end, okay? Because I just want to say certain things before.
Yeah, I'll fix it later.
Yeah.
Probably.
Right. So we have these, and so then you can just take as a definition, P is going to be the one truncation of this push forward. But to be precise, you have to do this as regarded as, okay, you have to modify it slightly, but maybe I just say the first words in these directions. So regarded as a sheaf on smooth rigid spaces over X. So you have to do some big side version of this calculation. It's not super important. I mean, the essential point is that the one truncation means you're talking about line bundles, and the R1 calculation is where the cotangent bundle shows up.
I don't quite understand. So you take this truncation, and then probably if you probably you are saying that if you look attentively at this truncation, you see the gerb, but
Right.
I don't see it at this.
So what? Okay, so let's say it carefully. So, I'm working in the category of etale sheaves on the big side of all smooth rigid spaces over X. On this side, this calculation will tell you that P sits in a fiber sequence where the right-hand term is the cotangent bundle twisted by -1, and the left-hand term is BGM. This corresponds to the fact that the H0 was OX star, and this corresponds to the fact that the H1 is the cotangent bundle. This is literally just rewriting the I equals 0 and 1 cases of this calculation. And now, since I'm working with smooth rigid space, so let me call this P prime, because this is not actually P. Since I'm working with smooth rigid spaces over X, this functor of taking differential forms receives a natural map from just the cotangent bundle of X itself. Given a differential form on X, I can pull it back to any smooth rigid space over X. And so formally, P is the fiber product.
So I didn't understand the details, but I think you are saying the following. So this truncation has I think you are saying the following. So if you have an object of the derived category,
Wait, is it getting it? I
What?
didn't hear anything you said because I think your connection dropped off.
Let me try again.
No.
Cohomology groups. And such a with two cohomology groups in degree 0 and 1. And then if you have such a complex, it knows a little bit more than the cohomology groups themselves.
Mm-hmm.
And then you are saying that if you look carefully at what it knows, then you get this gerb.
Exactly, yeah. Right. Okay, so that was the construction. I wanted to mention an alternative description which was suggested by Volodya in the case of GM, and also raise a question about yet another description. So Drinfeld's suggestion and we check that it works. Concerns the case of GM. So let's say X is GM. In this case, the cotangent bundle twisted by -1 is just, the cotangent bundle is just OX. So this is just X cross GA twisted by -1. And we're trying to describe an element of the Brar group of this cotangent bundle, and we're going to describe it as a cup product of two elements. And so the two elements are, one is, let me just call it alpha, alpha. Yeah, alpha is an element of H1 X ZP1. And this is the usual Kummer torsor, corresponding to multiplying by P to the N on the torus. And beta is going to be an element of H1 GA -1 with coefficients in mu P infinity. And this is going to be, actually, it's a multiplicative element. So it's going to be an extension, and it corresponds to the logarithm. So the logarithm for any rigid space is a map from 1 plus the maximal ideal times OX plus to OX. And the kernel is mu p infinity. Well, here I'm writing it in terms of sheaves on X. But if you think about the representing objects, then this OX is GA. And so this is an extension of GA by mu p infinity. And thus it defines an element of this group, at least, sorry, probably there should be no twist right now here. This is GA. And so we have these two completely natural elements. And so you can then contemplate where alpha cup beta would live. And so when I say cup, I mean I'm doing some kind of exterior product. Maybe it makes more sense to say box. I don't know. Well, let me just write cup. It lives in X cross GA with coefficients in mu p infinity of 1. But I can trade the 1 over to the other side. And so let me put that into my space. So it's better to think about it this way. And so we have now described some element in the mu p infinity cohomology of the cotangent bundle. And then the claim is that this maps to the class of P in the Brauer group. So this can be verified by a sort of a diagram chase that maybe it's not worth doing over here. But as Drunfeld said earlier, it's not so clear how to globalize this, how to say it without choosing coordinates. It would be very nice if there was. I definitely don't know how to do it. I wanted to just mention one other potential idea for getting an elementary description, which still doesn't quite work, but it feels like it has to work. And so this has to do with the Delaunay-Lozi picture. So we have this gerb of liftings of X to be theorem mod T squared. And this is naturally a GA gerb over the cotangent bundle. So let me just write this. So we have a canonical GA gerb. I don't know, PA for additive over T star X minus 1, corresponding to the obstruction to lifting X to this thickening B2C. I mean, this is this fancy pants way of saying something very simple, which is that this obstruction will be an element of H2 of X with coefficients in the tangent bundle of X twisted by 1. And if you write such an H2 as an X, then you can think about it as a gerb. But the reason I'm doing this is that this is a completely classical thing. All you need to know in order to write this down is this thickening B2C and some deformation theory. And then the basic fact is that the Simpson gerb is a lift of this gerb along the logarithm map. So claim is that P to T star X minus 1, which is a GM gerb, is well, it comes from a lift of this additive gerb, which is a GA gerb along the logarithm map, which is this map that showed up earlier, 1 plus m times OX plus to OX, which I think of as a map to GA. And so if there could be some pure thought way of explaining why a gerb banded by GA has a lift along the logarithm map, then we would also obtain a fairly classical description of the gerb. Unfortunately, I don't know how to verify this claim in some purely classical terms. The only proof I know involves thinking about the pro-étale site and the completed structure sheaf. And so this is mostly a question for the audience, which is there some simple words one can say to see why this gerb of lifting X to B2C actually has a quote unquote reduction of structure group to this object over here? I don't know the answer. And I wanted to say one last thing, which was in relation to Augus's question from before about this dual perspective. And so indeed, there is a dual way of getting at the Simpson gerb. It's beyond my pay grade, but I can at least tell you what I understand of it. I think there'll be further talks in Drinfeld's seminar about this kind of object. And so this is the ongoing work of Anschutz, Esteban Camargo, no, sorry, Rodriguez Camargo, I guess okay, Lebras, Rodriguez Camargo, and Scholze. There's a talk that Peter gave at a recent conference at the IAS on analytic prismatization, where you can learn a little bit more about it. But in relation to the material I was explaining today, I believe the picture is the following. And so what they construct is an analytic Hodge state stack. So a purely rigid analytic version of the Hodge state stack for formal schemes. This is not a stack in the usual sense in p-adic geometry, meaning that the rings you need to describe the stack are not going to be p-adically complete. So one needs an enlargement of classical rigid analytic geometry, and this is provided by this work on analytic stacks by Clausen and Scholze. So as an analytic stack. And the key features, so I don't really know much about this theory, but I can just push symbols around and I can tell you what the expectation should be, which is the following. So this stack is a torsor B under B TX dagger, where TX, okay, sorry, there should be a twist by one always when you put the tangent bundle. And so what is this TX dagger? It's the overconvergent neighborhood of zero. So a TX dagger is some kind of an intersection over all open subsets containing the zero section of that open subset. So it's there are no physical classical points on it, but it makes sense in this theory. And this is a torsor for this group. And so therefore, there's a classifying map from Z to B squared TX dagger, listed by one, corresponding to the analytic Hodge state stack. And then the expectation is that the Simpson gerb is the Cartier dual to this. So the class of P is, or I'll just write it in symbols, it's obtained by taking the previous map and harming it into B squared GM. So if you pretend that everything works without any technicalities, then harming into B squared GM will turn TX dagger shifted by one into the cotangent bundle twisted by -1. And it will turn Z into a B squared GM, and so you obtain a GM gerb over the cotangent bundle. So from this point of view, you gain something, which is you get a gerb banded by something that's that feels pretty quasi-compact. The price you pay is that it's not a classical analytic object. In the dual point of view, you get a gerb that lives over the cotangent bundle, which is not quasi-compact anymore. But what you gain is that now it's an object of classical rigid geometry. So this is my understanding of how this duality is supposed to go, but I've definitely not checked any of this. And I think this is all I wanted to say. So I'm going to stop now.
Any questions?
If I could just ask a question. So you mentioned the connection between the between the Simpson gerb and sort of formal scheme version that so I was just wondering, is there something that would do you expect that if you have a formal scheme that there's something that would specialize both to the gerb of differential operators on the special fiber and the full Simpson gerb?
I don't know such a thing. I mean, I think the best I can imagine, at least if the kind of object you want is something that lives in formal geometry, then I think the answer is no. Because then the best thing you could hope for is that it lives on the cotangent bundle of the formal scheme, which only gives you the radius less than or equal to 1 part of the generic fiber. I was discussing this briefly with Peter when he was here, and he was suggesting that if you just give up on formal geometry and pass to analytic geometry, there might be a positive answer to this question. But yeah.
Question related to the explicit construction of the gerb in the case of the multiple. Do you hear me, by the way?
Sometimes. There are
Hello?
dropouts. There are
With the
dropouts.
I have a question, but since the devil works against me, I will send an email to Bhargav.
Okay.
I can just
The devil is against him.
And can you explain meanwhile why if you have a lift of x over b-theorem plus modulo t squared, then the map from x to bgm, from the cotangent space to bgm, factors through b2 factors through b2 mu p infinity.
So there's a right. It's a diagram of exact sequences, which gives this to you. Maybe I can try to draw. I can try to draw it here. So, okay. Let me try to remember how it goes. So you work with 1 plus m times ox plus hat. And this has this logarithm map to ox hat. And the kernel is mu p infinity. And this mu p infinity, on the other hand, maps to gm. And what was I going to say? Oh, yeah. And then over here, you have ox hat star. This is the obvious map. If I remember correctly, the cofiber of this, by Ben's calculation, is tau bigger than 1 of ox hat. So this is kind of the key diagram. This is the usual logarithm sequence for the completed structure sheaf, but pushed forward to the etale side. And this is Ben's calculation. And so now, if you have a omega 1x minus 1, which is the first cohomology sheaf of this complex. So actually, let me also put, let me imagine x as a curve. So everything is 1 truncated. Otherwise, I have to put a 1 truncation everywhere to make what I'm saying correct. But let's assume this is, say, x is a curve, just for simplicity. And then these two would be the same. And now, if you have a choice of lift of your curve to b-theorem mod t squared, you get a splitting like this. And so then you stare at this picture and you see that as a reduction to mu p infinity. I mean, this over here is sort of the gerb we were talking about, and I reduce the structure group to mu p infinity. Sorry, does that make sense?
Just a second. So you have a map from OX star to tau greater or equal than 1 of OX hat. What is this
Oh,
map?
this is by Ben's calculation, right? So a priori would go to tau bigger than 1 OX hat star,
Yes.
but Ben says that that's the same as what happens additively.
Right. Did you explain? I think I asked before if you could explain either this calculation or Schultz's calculation with the additive version. I don't think you did that yet. Is that right? Or did I
I
just
definitely did
forget?
not explain Schultz's calculation with the additive version, because that's
Is it difficult? Can you give a brief idea how that works? R1V lower star O being omega 1.
so the hard part is to define the comparison map from differential forms
Yeah.
in. And one way to get this map would be to use the, well, sorry. So you looked at, since I'm answering Arthur, I can use knowledge about the question asker. So I know you looked at the Prisms paper, and in the Prisms paper, there's a formal construction of a comparison map from differential forms to the Hodge-Tate complex, to the cohomology of the Hodge-Tate complex, because one thing has a lift to A and therefore you get some CDGA structure, and then the universal property of differentials will give you a comparison map. And you can say the same words over here, where the lift to A is now replaced by a lift to B to ROM.
Okay.
I think probably a better answer to your question would be that maybe if X has a good formal model, then this is the same as the Hodge-Tate comparison for the formal model.
Okay.
This can be recovered from that.
Okay. I have a remark that has nothing to do with your talk today, but has a tiny bit to do with that paper, which I'd like to make if it's appropriate at this time. I'll probably wait until more questions about this talk are finished with.
Maybe I just want to make sure Vadim understood or was happy with what I was saying, or I can re-explain this diagram.
Yeah, thank you. Yeah, I think I understand. Yeah, thank you.
Can I also ask something? So I think like in this article by Liu and Zhu, and then they have this notion about p-adic Riemann-Hilbert, which kind of deforming their version of p-adic Simpson correspondence. I'm kind of wondering that if you're like the equivalence that you described here can also fit or relate to a certain Riemann-Hilbert correspondence in some way.
Right, that's a good question. So I think I don't know what to formally say on the other side. Like, I think the category you're talking about is like pro-étale vector bundles, or equivalently these twisted Higgs bundles, which lives over OC. And this has kind of a natural p-adic thickening given by doing sort of coefficients in beta rom mod t to the n. But I don't know kind of a spectral realization of this category as like coherent sheaves on some geometric object. Like mod t, it was these twisted coherent sheaves on the gerb. I don't know how to deform that mod t to the n. The picture in terms of the analytic Hodge-Tate stack, I believe, does deform. So I believe my understanding is that there's supposed to be just an analytic prismatization which lives over, in particular, over beta rom plus, but in fact over something bigger.
Okay. Thanks.
I have a question which is somewhat related to your talk. Is there a description of the group X from GA to GM in the analytic setting? In other words, look, suppose I want to describe all extensions of the analytic additive group by the analytic multiplicative group. And maybe one would like to have such a description with parameters. In other words, suppose that we
Is it
consider
x1 or higher x as well?
what?
Are you interested in all x groups or just the first couple?
Maybe, well, maybe x2 as well, but especially x1. And I think it's related to if we want to construct
Right.
such the gerb, that the Simpson gerb, then it's natural to ask about such extensions.
That's right.
I think there are no x0, x1.
No, just no. There is an x1
No, there's an
because
x1.
you have just a moment. What about the logarithm? The logarithm,
Exactly.
no, the logarithm.
No, but the logarithm is an x1 from GA into mu p infinity.
I see. But then, okay.
I believe so.
But maybe one should do this with parameters, so to say. Probably it's a reformulation of the problem, and maybe it's related to Ben Hoyer's crucial computation. But maybe if you think in terms of such extensions, there could be a more transparent way of understanding his computation and Scholz's computation.
Sorry, I just wanted to say that I think if by parameters you mean doing it over some base.
Maybe a smooth base. Suppose you have a base, for instance, a disk.
Right. So my impression is that over a smooth base, the functor of units and the functor of line bundles are both A1 homotopy invariant. And so I think that would imply that there are no x0 and x1. I can check that and get back to you. I think that's true.
Other questions?
Oh, I have one. Sorry. So I have one more small question. So I think I was kind of wondering, like the equivalence that you and Minjia produced in p-adic story. So is there also kind of certain gerb in a complex story which producing a correlate Simpson correspondence?
I have no idea, but I mean, that's a bit similar to asking whether this, I mean, there's the first step of the construction, which was going from local systems to pro-étale vector bundles. And the gerb came in and trying to understand pro-étale vector bundles. So you can ask if the first step has a complex analog, and I mean, it would, depending on how we formulate the question, the answer would obviously change, but Dustin gave a pretty convincing reason why this cannot have a good answer, which is that the only reasonable notion of a perfectoid space over the complex numbers would have to be a compact Hausdorff space. And the reason was roughly that, like, perfectoid space, at least pro-étale locally, they're these strictly totally disconnected guys. So you can think about them as sort of profinite sets worth of algebraically closed p-adic fields. Complete algebraically closed p-adic fields, but a complete algebraically closed real field would have to be the complex numbers because of some classical result, maybe by Gelfand. And so that means that you would only ever run into continuous functions on a compact Hausdorff space as your algebra of functions, and so you only see compact Hausdorff spaces as the analog of perfectoid spaces, and that's not enough to recover coherent sheaf theory.
So it's not clear if there's any kind of direct analog in complex theory for this entire picture. Okay, thank you.